Hello everyone, I am pleased to present our CVPR work BI-CIMP stereo, bidirectional cross-modal prompting for event frame asymmetric stereo. This work focuses on stereo matching in an asymmetric cross-modal setting, where the two views are captured by different sensors, a conventional frame camera and an event camera. Instead of treating this setting as a simple feature fusion problem, we aim to explore how the two modalities can effectively interact with each other while maintaining their own distinctive properties. To this end, we propose BI-CIMP stereo, a bidirectional cross-modal prompting framework designed for robust and accurate disparity estimation. In the following presentation, I will first introduce the motivation and challenges of event frame asymmetric stereo. Then, I will explain our proposed CIMP stereo and BI-CIMP stereo frameworks, followed by the experimental results on DSEC and MVSEC. First of all, let me explain the motivation and key challenges behind this work. In stereo perception, conventional frame cameras are widely used because they provide dense appearance information, including texture, structure, and semantic cues. However, frame cameras can suffer from motion blur and degraded image quality under fast motion or challenging illumination conditions. Event cameras, on the other hand, have very different sensing characteristics. They respond asynchronously to brightness changes with microsecond-level latency and a very high dynamic range. This makes them particularly suitable for dynamic scenes, low-light environments, and high-speed motion. However, event data is also sparse and asynchronous, which makes it difficult to directly use standard stereo matching techniques. This naturally motivates the setting of event frame, asymmetric stereo, where one side uses a frame camera and the other side uses an event camera, compared with a full event-based stereo system. This setting is more cost-efficient while still benefiting from the complementary properties of the two modalities. However, the main challenge lies in the cross-modal gap between events and images. Since they have different sensing mechanisms and different data distributions, directly aligning their features can weaken the correspondence between the two views. More importantly, many existing alignment strategies tend to suppress domain-specific cues, which causes information loss and limits the final stereo accuracy. To address these challenges, our work makes three main contributions. First, we propose CIMP stereo, which introduces SCC and CDEA to preserve domain-specific features while achieving high-fidelity cross-modal alignment in a target canonical space. Second, based on this design, we further introduce BI-CIP stereo, a bidirectional framework that integrates complementary information from both the event and image domains. This allows the two modalities to enhance each other instead of forcing them into a single homogeneous representation. Finally, extensive experiments on the DSEC and MVSEC benchmarks show that our method significantly outperforms state-of-the-art approaches in terms of both accuracy and generalization. Now let me introduce the overall architecture of our proposed cross-modal prompting stereo network, or CIMP stereo. As discussed in the previous slide, the key challenge in event frame asymmetric stereo is the large cross-modal gap between events and images. Therefore, the main goal of CIMP stereo is to align the two modalities effectively while preserving their domain-specific information. In our framework, we consider two asymmetric input settings by alternating the input roles. In one case, the event modality is used as the target domain, which we call FCIMP stereo. In the other case, the image modality is used as the target domain, which we call IMGC-IMP stereo. This design allows us to study cross-modal prompting from both directions. Given the source and target inputs, we first use the cross-domain embedding adapter, or CDEA, to adapt the source domain embeddings toward the target domain. After that, we introduce the stereo canonicalization constraint, or SCC. The purpose of SCC is to map both the source and target domains into a shared canonical space for stereo matching. This helps build more reliable correspondence between event and image features, while avoiding excessive suppression of their unique information. In addition, we apply hierarchical visual transformation, or HVT, during training. HVT provides context-level regularization and improves the generalization ability of the model, especially when facing different scenes or domain variations. Finally, after constructing the cross-modal matching representation, we use cascaded conv-GRU modules to progressively refine the disparity map from coarse to fine. This coarse-to-fine refinement strategy allows the network to recover more accurate disparity details. Based on the single-direction CIP stereo framework, we further extend it to a bidirectional cross-modal prompting stereo network, namely BI-CIMP stereo. The key idea is that event and image modalities should not be treated in only one fixed direction. Instead, each modality can provide complementary information to the other. Therefore, we construct two single-domain CIMP stereo branches with opposite target domains. After obtaining the two canonical representations, we build multi-scale cost volumes in both the image and event domains. These cost volumes encode stereo matching cues from two complementary perspectives. Then, we fuse the dual-domain cost volumes in a multi-scale manner. At coarse scales, we concatenate the cost volumes from the two domains to combine their complementary matching cues. At the fine scale, we further use a 3D hourglass network to aggregate the fused cost volume and enhance the final correspondence representation. Finally, the fused representation is passed into the cascaded disparity refinement module, which progressively refines the disparity map from coarse to fine and produces the final prediction. Overall, BIC-IMP stereo allows the model to exploit both image-guided and event-guided matching cues. Instead of relying on a single canonical space, it learns to distinct but complementary canonical spaces, leading to more robust and accurate disparity estimation in event-frame asymmetric stereo. Now, we evaluate our method on the dissect benchmark, which is a challenging real-world dataset for event-based stereo perception. The upper table reports the quantitative comparison with several state-of-the-art stereo methods. We evaluate the performance using multiple metrics, including IMAE, 1-pixel error, 2-pixel error, and RMSE under different scene conditions, as shown in the table, both single-direction variants. FCIMP stereo and MGI-CIMP stereo already achieve competitive results compared with previous methods. This demonstrates that our cross-modal prompting strategy is effective for reducing the event frame domain gap. More importantly, the proposed BIC-IMP stereo consistently achieves the best overall performance across most metrics. This confirms that using bidirectional canonical spaces can better exploit the complementary information from both the event and image domains. The lower part shows qualitative comparisons. Compared with previous methods, RBI-CIP stereo produces more complete and sharper disparity maps, especially around object boundaries and challenging regions. Next, we further evaluate the cross-dataset generalization ability of our method on the MVSEC dataset. As we can see, our method achieves the best overall performance across all metrics, showing that the proposed bidirectional cross-modal prompting strategy is not only effective on DSEC, but also generalizes well to MVSEC. The qualitative results at the bottom further support this conclusion. Compared with previous methods, our method produces a disparity map that is much closer to the ground truth. It better preserves the object structure and provides smoother yet more accurate depth estimation in challenging indoor scenes. Overall, the MVSEC results demonstrate that our method has strong cross-dataset generalization ability. This indicates that learning complementary canonical spaces from both image and event domains can improve not only accuracy, but also robustness under dataset shifts. Thank you very much for your watching.